Okay, it looks like we're live. Cool. Um, all right. Well, I guess we'll just dig into it. It's great to have you back. Thanks everybody for joining me again for session 2 here of the workshop on writing code, approaching programming as just another kind of literary practice or writing practice. So today we've got a whole bunch of stuff to cover. I feel like I packed way too much stuff in here today, but we'll see. I'm just going to try to power through it. And we have a surprise special guest and some other fun stuff to look at. So we're going to start off by looking at the results of last session's experiment. So this is your homework that some of you shared, uploaded some stuff into the shared Google Drive that we have that is linked on the Patreon posts. So let's take a look at what you all did with this. Remember the prompt here was to try to do some storytelling in a meta language. So we were looking last time at some people like for example Vladimir Propp, who wrote the Morphology of a Folktale, or Morphology of Russian Folktales, I think. And we looked at, and that was a kind of like structuralist approach to taking a story, in this case a bunch of folktales, and sort of deconstructing them, and finding out what are the common, what sort of like common functions and properties do they have between them, so that we can devise like kind of a meta language in order to talk about these stories, or in order to just communicate these stories. So let's start here with Bjorn. This one from Bjorn was so your prompt here was to take an existing story or write your own story and then kind of rewrite it in a meta language, or in other ways abstract it once or more and try to get it as abstract and general as you can. Bjorn looked at 2 films, The Princess Bride and Memoria. These are 2 like very, very different films. I haven't seen Memoria, but it looks and sounds like incredible. So thanks for introducing me to that one. I hadn't heard of it. The sound design in the trailer that I watched was like super wild. So I'm definitely going to check this film out. Just real quick, Bjorn sort of wrote this summary, and this actually the language that he's using here reminds me a lot of Vladimir Propp's Morphology of the Russian Folktales. A princess falls in love with a farm boy, and so on. We've got these like archetypal kind of character descriptions, and this is a sort of a structural summary of the plot. And then, meanwhile, Memoria, which is I think Bjorn said in their notes that Memoria is like a sort of plotless film, or at least that was their experience of it. Memoria, however, has this sort of, so here's a plot summary of it. A woman finds her life interrupted by unexpected eruptions. She travels into the forest and discovers a wise man, and the wise man reveals the truth to her. So that's like a sort of plot summary, right? But then over here, Bjorn did another take that is just a series of images. A skull has been buried beneath the ground for ages. Outside, car alarms go off, and so on. These are just like these sort of little pictures of moments, and a lot of films can be described in this way, as a sequence of pictures rather than as a sort of set of plot points or something about archetypal characters or something. So I thought that one was pretty cool. This is one by Brad Garner, which was, this one was, Brad took it through several steps. And this one I think was, if I recall correctly, the only one that was a text that Brad wrote himself, so not like a film or a story that they found somewhere else. So we can see, and if you look in the Google Drive, these are all in there too if you want to look at them in more detail, but you can see Brad kind of removing details. This is something that I noticed in this one. It's like this is really a process of removing details, which is what we call abstraction, right? Removing sort of details that we determine to be unnecessary for different kind of ways of looking at something. And it's kind of interesting to see, like which details Brad chose to keep and which they chose to remove. And by the end here, it's just a great teacher visits an ancient village over and over for 20 years. But in the beginning, it's like you sort of have to read between the lines to pick this up, that this teacher is visiting this village repeatedly, because in the beginning, it's in the first draft, Brad's sharing like these details that paint a picture of this story here. But by the end, it's just the story itself directly. So it's kind of an interesting take. And then here was one by Aaron, This was a summary of the film Upstream Color that I think Aaron said, yeah, they took from the plot summary from Wikipedia, which somebody, one of Wikipedia's cranky editors had said that the plot summary was too long or excessively detailed. So thanks, Aaron. Maybe you can contribute this back to them as a less excessively detailed summary. And this again, I have seen this film Upstream Color, and it's a really difficult one to get your head around the plot. There's very little dialogue, if I recall, in this film, and you sort of just have to watch these events unfold, and you really have to put them together to figure out what their relationship is. This is a film that's really less about a story and more about just like an ecosystem, a sort of ecosystem that crosses over between biology and personality and social relationships. And here in version 2, Aaron's condensed this down to 2 sentences. The thief and the musician are reliant upon each other. Their relationship takes advantage of many until 2 victims are able to put a stop to it. So that actually just that's a good plot summary of the film. But yeah, I like this first one, especially. A thief hypnotizes her with worms. That's just a great phrase. Okay. Let's move on. And also is literally what happens in the film. Travis Foster shared this one. This is based on an excerpt from a nonfiction book by John McPhee called Basin and Range, which is, I think, I looked it up, and I haven't read this, but it sounds really interesting. But I think it's like interviews with geologists and also with just people that live in this area, the Basin and Range area, which is like the Southwest, I think. So let's see. Yeah, we can see in these iterations. So the first sort of draft of this, or the first iteration, again, is like kind of paints the picture of a story with a bunch of details, and including like some word-for-word dialogue, like some quotes from the people that the author was talking to. And by the end, and then in the second iteration, you can see something that they did here, which is a switch to describing the story in a different way. Instead of sort of relaying the events of the story, we switch here to describing, I guess, like sort of how the story was written. The writer describes this, and then, later the voice of a geologist identifies this, and so it's kind of zoomed out a little bit. And then in the third iteration, this is not a description that's grounded in the book. This is a description of the actual sort of events that the book describes, which are events on a geological timescale, 20,000 years and millennia of silent, slow erosion, and so on. So it actually also zooms way out from these like human scale, timescale details out to geological time. This was a good one from Lizhu. This is a poem by Gertrude Stein that, who was this great modernist poet from the early 20th century, right? Who wrote with like lots of repetition and very, very conscious of sound in her writing. And so Lizhu describes their process here and basically took that poem and then used this markup system that they devised to replace some of the words with markup that sort of describes it sonically, basically, like identifies these 2 slashes kind of bracketing one of these words, identify it as a sort of an anchor point in the rhyme scheme. And then in the next iteration, they replaced some of the words that are not sort of like emphasized in the rhyme scheme, replaced those with logical symbols that I at least have a pretty easy time recognizing. Like here's the house was just twinkling in the moonlight, and inside it twinkling with delight. And so they've replaced and inside with this plus plus. So I can kind of see some kind of relationship. And then here was replaced with this equals equals. This sort of like condensing some of the. Oh, here's the 3 dots. That's a logical symbol. I forget what that means. But so yeah, sort of condensing the language itself down into a more like into a tighter language. But it also, by using these this markup, you can kind of look at this visually, and it sort of has the same effect as listening to it. Where it emphasizes the rhythm and the kind of musicality of it, because we're looking at these shapes and changes of shapes over time, over the duration of the line, just as we're kind of like listening to changes in the sound of the words in the original poem by Gertrude Stein. And I put this in here as a comparison. This kind of reminded me, Lizhu's approach here kind of reminded me of one of my favorite poets, Mez Breeze. This is from Australia, I think, if I'm remembering that right, who has been working in this kind of like code poetry intersection for many years at this point. I think her first work was like in the mid 90s. It's kind of part of the like early net art movement or web art movement. So she draws a lot on the language of what are called regular expressions, which we'll get to that later in the session. What regular expressions are, not in this session, but in another course. And using this language of regular expressions, which is about matching patterns in text, she kind of writes these poems that to me they read as if they're in a fictional programming language, which called Mesengel. That's the name she's given to this like fictional programming language that she writes in. But they also have this really interesting sort of vertical layering of words because of these components that are encapsulated in brackets that can kind of sometimes they'll have like multiple options for a piece of a word or something, so that you can kind of read the poem vertically, not just horizontally, but vertically, if that makes sense. Not vertically on the page. I mean vertically like there's concepts stacking up, multiple concepts in the same time moment. Vertically in the sense of like music, like harmony in music. But yeah, so I thought, that was really nice work, Lutzu. Something from Selva or Chelva. I'm not sure how to say that. Maybe if you're Italian, we'll say Chelva. But Selva put a few different things in a PDF in the Google Drive, and I recommend you take a look through. There was some stuff based on or sort of referencing KRZ in there. It was kind of fun. And also this one I really liked. This is a blurred version of a photo. Maybe blurred photographs are also a way to remove extra details and save the vibe or mood or feeling. And yeah, I think that is kind of interesting. I kind of, for me, connected that with this this thing that Ludwig Wittgenstein said, this philosopher Ludwig Wittgenstein, who we're going to talk about a lot more today. And he asked, is an indistinct photograph a picture of a person at all? Of course it is. Is it even always an advantage to replace an indistinct picture by a sharp one? Isn't the indistinct one often exactly what we need? Kind of interesting. We'll come back to that. Here's another one. This is two summaries of the anime Mushishi. So again, we've got this is sort of a plot summary, or is this sort of like plot-oriented summary, and then this one is a series of images again. It's kind of poetic, and again, yeah, there's really it's interesting that you can abstract things, the same thing, in so many different ways, and kind of like reproduce the same story in some way from so many different meta languages that you can devise. And then here's this calendar, the months from January to June, and then rewritten based on how they feel, which I liked that little drawing. Okay. So this one's from Kurt Remke. This is a piece, a fragment from a book by William Least Heatmoon, who also wrote, was it called Blue Highway, I think? I haven't read that, but it's been recommended to me by a number of people because of some correlation with Kentucky Route Zero, but I really want to read it. Anyway, in this one, let's see. Yeah, right, yeah, so he went and again sort of like summarized the story multiple times. Right, so we've got, at this point, yeah, this is a man recalls memories of the Dust Bowl in Colorado. He remembers, so we're kind of like, this is a narrative of what's happening in the story. And then down here, we're moving down into like talking about the writer and what the writer is doing. This is another way of like kind of zooming out and describing the story. And then why did I paste this one? Yeah, sorry, I forgot what I had to say about this last fragment. But yeah, thanks, Kurt. That's another great one to check out. Awesome. So, sorry if I'm moving really fast. I just have so much stuff I want to get through today. But thank you so much for sharing your work. And I hope that I got everybody this time. But if not, I apologize. I'll take another look in the folder. But yeah, I really appreciate you all throwing something in there, and I'll have some more homework for you at the end of this session. So this session's called Fiber on Fiber. So last month, we talked about this writer, or this programmer, I should say, Christopher Strachey, who and his we looked at some of his artwork that he made and some of his programs that he made, and also talked about this idea that he sort of initiated this kind of research project that he initiated into the semantics of programming languages. And Strachey's approach to the semantics of programming languages was something that we now call denotational semantics. So I'll go down here. Oh, yeah. Okay. And this is a little fragment from the first paper where he introduced this idea. At that time, he didn't call it denotational semantics yet, and it wasn't really very rigorously formulated. Eventually, he started collaborating with this mathematician named Dana, logician named Dana Scott, who helped him. Together, they developed a sort of like rigorous mathematical foundation for the study of the meanings of programming languages. But I just got this book, and I just wanted to share it because I'm really pleased to have finally found it. And this is a collection of this is basically the proceedings from this conference called Formal Language Description Languages from 1964. And this was the conference where Strachey presented this paper. And so I've been trying to track this down because I couldn't find it online anywhere. And it's really, I just really wanted to see, when Strachey started talking about this, like how was he talking about it? So at the time he was just calling it formal semantics. And this is what he wrote in the opening. So, a programming language is a large body of new and somewhat arbitrary mathematical notation. Already, he's saying, okay, a programming language is mathematical notation. This was not the consensus at the time that he gave this paper. In fact, I think the only way to read this is that he was sort of, he's trying to start an argument. It's polemic, because looking through the rest of this book, all the other presentations, all the other sort of lectures that are about semantics of programming languages are all strictly, again, in terms of this like operational model of like thinking about a machine, right? So he says, no, a programming language is a large body of new and somewhat arbitrary mathematical notation. The syntax and semantics of these languages are nothing more than the rules for using this mathematical notation and for interpreting it. Together, the syntax and semantics of a programming language should define it precisely. They should make it possible to determine if any particular piece of text is a program in the language, and also determine what the outcome of any well-formed program should be. And then he says you could think about that by splitting those two things apart, splitting syntax and semantics, and saying syntax is the rules of like how the first part, like how we recognize is this piece of text in the language or not. And then the second part is like, what does this program do? That's the semantics, and that's a standard way of splitting it up. And he says that's really useful for people who write compilers, which are the pieces of software that translate text into programs, right? Compilers. He says that's really useful to think about it this way for people who write those programs, compilers, because that's what a compiler does. It first looks at the string of text and says, is this in the language that I'm trying to compile? And then it looks at some kind of semantic model or interpretive program in order to determine what the outcome should be. And he says, I didn't highlight this part, but Strachey says, but most people who are like writing code, like programmers, prefer to think about this more synthetically. Instead of splitting these two things apart and saying, you do this step, you check if it's in the language, and then you run the program. Instead, most people, would really prefer to think about it that semantics is what you want to say, and syntax is how you say it. And then I would say poetics then is the play between syntax and semantics, between content and form, right? And Strachey goes on, unfortunately, the fact that syntax is easier to understand and to formalize, especially to formalize, has meant that a great deal more work has been done on it than on semantics, so that to all too many onlookers unable to see the semantic wood for the syntactic trees, they've gathered the impression that syntax is the be-all and end-all of programming languages. On the other hand, the most basic concepts of programming languages, distinctions between names and values, for example, are very rarely discussed, not because they're generally understood, but possibly because most people find them confusing. Yeah, anyway, that's just to kind of bring back the Strachey perspective on language. So let's say, yeah, syntax is kind of overly represented in learning how to program. If you, a few years ago, I decided that I wanted to learn how to make programming languages. So, I got some books and I did some Googling, and every single tutorial or book or anything, and I just checked this again. I went back and looked at every tutorial or programming book that I could find about how to create a programming language. Every single one of them followed this pattern. it said that the first thing you do when you're going to make a programming language is you build what's called a tokenizer and a parser. You define the syntax, and then once you have the syntax being read by this parser, and it has the syntax, it's like meaningless at this point. It's just being read and turned into some kind of abstract syntax tree, some like computer model of the syntax itself with no reference to its meaning. Then you can start the process of building your program and determining, how this language interfaces with your program and basically what this language does. That's almost universally the case, the way that this stuff is approached. And the semantics are, if they're presented in any kind of formal or formal way or with any kind of depth, it happens much later and usually doesn't happen at all. So let's talk today a bit about semantics, about meaning, right? And let's look at a few different kind of like ways that different philosophers and writers and people have tried to use language to construct meaning. Because there are a number of radically different ways to do it, and there's really no consensus on what's the right way, and usually we end up doing several of them at once in natural language. I'm going to talk about natural language at first, and then of course programming languages are not natural languages. They're quite different, but they're all languages, so we can use this information. Okay, so the first philosopher we're going to talk about is Humpty Dumpty. This is from Lewis Carroll's Through the Looking Glass. So Humpty Dumpty is this egg that Alice finds in this, in Wonderland, and he turns out to be a real asshole. And they've been having this argument, Alice and Humpty Dumpty, and he used some word. I think he said, "Oh, that's glory for you," and she's like, "What do you mean by glory?" And he's like, "I meant that's a really good argument." She says, "I've never heard the word glory used that way." And Humpty Dumpty says, "When I use a word, it means just what I choose it to mean, neither more nor less." Alice says, "The question is whether you can make words mean so many different things." And Humpty says, "The question is which is to be master, that's all." He's like, "You gonna let a word boss you around?" And then he goes on to talk about which of the different words are more or less easy to get along with. I think it's like, nouns will follow your directions, but verbs can be very difficult and they don't listen very well. So this is a theory of meaning in language that's called connotation. That's how it was described to me in when I was in high school. But as far as the meanings presented here, another way to talk about them is that they are intentional. And so that's that word intentional. It's not intentional, right? Thanks, English. It has an S there instead, but it's very similar, and it's about this idea of intent. So an intentional meaning of a word is really like what Humpty Dumpty's doing here. It's like when I tell you, bring me an apple, and you bring me a rotten apple, and I say, that's not the apple I wanted. That's about the intentional meaning of the word apple in that case. That I meant like, I want you to bring me an apple I can eat. And another way of describing that is that the connotation of the word is that I want it to be something that I can eat. I want a snack or something. So you can imagine how misunderstandings arise when we're using an intentional approach to language and meaning. Because you can't read my mind, and Alice can't read Humpty Dumpty's mind. She doesn't know what meanings he's arbitrarily attaching to these words, right? So the opposite of intentional definitions are extensional definitions. Okay? The extension of a concept is everything that concept covers. Okay, so the extension of the concept for is like everything that numbers for. If I put 4 rocks down in a row, the extension of the concept for covers those. The intention of the word for might not cover those rocks, because in the moment that I said 4, it might be because somebody was asking me, how many tires do you want on your car, or something like that, right? So that's the difference between extensional and intentional definitions. And the way that this was presented to me when I was in school was connotation versus denotation. And this is the same denotation in denotational semantics that we're going to look at. So the denotation of a word is like it's sort of objective meaning, right? And not just its objective meaning, but maybe objective is the wrong word. It's its extensional meaning. so it covers like if I'm saying, well, here's a good example. I just searched for like dictionary because and it happened to be a screenshot of the entry for surrealism here, a photo of the entry for surrealism. So if I'm watching a film, if I tell somebody I want to watch a surrealist film, there's a way that like the denotation of the extensional meaning of the word surrealist, might refer to this movement in the arts or something. If I watched a film and I say that was surreal, I could mean like a lot of different things by that. And I might, at some level, probably I am using the denotation, the extensional meaning of surrealism. I am probably saying like it has something to do with this art movement. But I might also just be saying it was kind of dreamlike, which is related to that movement, in fact. Or I might just be saying it was weird. It can have a lot of different connotations to that word, and it might have different connotations for different people. And that's again, that's where confusion arises. Where does confusion arise with extensional definitions or extensional meanings or the denotation, the definitions of denotation? Well, there might be different I guess there might be different sort of like sources of authority on the denotation of a word, for example. But it's definitely less prone to confusion in the way that it's kind of formulated here than is the Humpty Dumpty approach. I said we were going to come back to Wittgenstein. We're going to see this guy a couple times today because he went through a lot of different versions of his ideas over his life. So this is the early Wittgenstein. The early Wittgenstein said language is a logical picture. So, a watercolor is a picture made out of colors, right? A photograph is also a picture made out of colors and values. Language is a picture made out of logic. So you look at a painting or a photograph with your eyes, and, language you sort of look at with your mind. He wrote about this in a book called the English translation of it. The title is actually in Latin. It's Tractatus Logico Philosophicus from 1921. This is a really strange book. It's sort of like it's either philosophy or modern poetry or modernist poetry, or sort of like both. And it's a sequence of these little. It's a sequence of these numbered propositions. I think he called them propositions, if I remember right. And you can see they're like really, really fussy, scientific, like very hierarchical. In fact, they're so hierarchical. This is something that somebody from University of Iowa made that sort of outlines the Tractatus as if it looks like a subway map. But you can see how there's basically 7 main propositions. Statements, I forget exactly what he called them, and then each of them has all these little branches, and those have little branches, and so on. It's this highly structured, crystalline, idea. And this was from a time when Wittgenstein was he was really young. I think he was like 30 when this came out, and he was really influenced by this group of philosophers working at the time that were called we call them now like the logical positivists. So these were people who were like, we need to come up with a formal language of logic that is totally denotational, right? That is totally all about extensional concepts, where we can get rid of intension completely, and also where we can get rid of metaphysics completely, right? So metaphysics is that area of philosophy where we try to produce synthetic knowledge from our thinking, from concepts that we have in our head. We try to think up new knowledge. That's as opposed to other kind of like phenomenological kind of studies, where we're using observation and stuff like that to come up with knowledge, basing things in facts and empiricism. I think empiricism is the opposite of that logical positivism, right? But yeah, it's an interesting book though, because he also was I love his writing, and it's very poetic, this book. And in the middle of writing it, World War I broke out, and he went and fought in World War I, and had a terrible time, of course. And it changed. He came back and he had finished this book, is my understanding. He finished it like basically in the trenches. And when he left, he was working with Bertrand Russell, who's like mathematician and logician who, very famous, of course, and philosopher, whose project at that time was looking for a new foundation of mathematics after he had found some logical contradictions in the foundations of mathematics that they had been that were popular in the late 19th century, the set theory. So a very formal, again, very logical kind of project that Russell was involved in, and that Wittgenstein studied with him and was learning about this. But his experiences in World War I, I guess, sort of put things in a different perspective for him. And this book ends with this statement, whereof one cannot speak, thereof one must be silent. He brings it up in the introduction to here, where he says, the whole meaning of this book can be summed up as what can be said at all can be said clearly, and whereof one cannot speak, thereof one must be silent. He says at the end here, my propositions, he's talking about the book that you've just read. This is the very end of the book. My propositions are elucidatory in this way. He who understands me finally recognizes them as senseless. When he's climbed out through them, on them, over them, he must, so to speak, throw away the ladder after he's climbed up on it. He must surmount these propositions, then he sees the word rightly. So he's basically, he's saying, you need to read my whole book of logical positivism, and at the end you will understand that nobody can actually say anything sensible about philosophy. Truth, beauty, things like this are beyond sensible speech. Anything we say about these things is nonsense. And he makes this appeal, whereof one cannot speak, thereof one must be silent, and that's the only one of these propositions that has no subpoints. So I've always really enjoyed the poetics of this piece. Yeah, Brad says 20th century philosophy went in lots of different directions. It's really true. This is pretty wild stuff. But this is the early Wittgenstein. We'll come back to Wittgenstein in a minute, and we'll see what he was thinking late in his career, because it was very different. First, I'd like to, in this, in the context of this Tractatus, I'd like to ask you, what's something that you cannot express with language? You, the royal you, what's something that cannot be expressed with language? If you want to put your thoughts in the chat, we'll come back to this in a little bit. So for Wittgenstein, it's anything that can't be a logical picture, anything that's beyond logic, in this very narrow sense, is inexpressible with language, and most of what we say is nonsense. So what do you think cannot be expressed sensibly with language? I probably should have said. Okay, so here are some other 20th century ideas about language and meaning. This was a very popular one, behaviorism. And this one, I think, is kind of from the 40s, 50s, something like that, maybe even 60s. This is mostly popularized by B.F. Skinner, who is famous for applying the ideas of behavioral conditioning to basically everything. Skinner, we have the phrase now, a Skinner box is something like this situation here of Pavlov's dogs, where the bell is rung when the dog is being fed, and thereafter you can just ring the bell without any food and the dog will start drooling. Later in his life, Skinner applied this principle to everything. He wrote a book called Walden 2, it's a fiction book. It's like a utopian fiction about his vision for a society that's all based on this principle of behavioral conditioning. Sounds pretty horrific to me, but it was utopian to him. And actually, if you played Kentucky Route Zero, there's a lot of references to that book in Act 5. It's sort of about the people of nothing, the sort of utopian community are modeled after Walden 2. There's some references to Skinner in there. He said it later in his life in this book called Beyond Freedom and Dignity. Man's struggle for freedom is not due to a will to be free, but to certain behavioral processes characteristic of the human organism. Not my favorite approach to meaning, but he basically says, if you say something, it's because of some conditioned response. It's biological. You have no control over it. And it's kind of senseless to talk about meaning in this context, I think. Another important philosopher of language in the 20th century was John Austin, who wrote this book called How to Do Things with Words. Actually, he didn't write this. It's lectures he delivered, and it was transcribed by his students. So in How to Do Things with Words, Austin focuses on what he called speech acts. These are things like saying, I hereby name this ship whatever, or I promise to go to the grocery store tomorrow, or giving an order like shoot this person, I guess is the one he came up with. These are speech acts, are like things that we say, ways that we use language to like actually do things. They have this, I promise, is actually a social, you've established a social contract by saying I promise. So it's not just that, this, however, France is hexagonal. That's not an act. That's a proposition that can be true or false. France is hexagonal. We could perhaps say that the act here is making a claim, or perhaps asking a question or something. So Austin didn't say that speech acts are the only type of speech, but he said speech acts are a sort of like underexplored category of speech, and this book is his lectures about this category. Austin was very influenced by the later Wittgenstein, who we'll talk about in just a second. Actually, right now. So later in his life, Wittgenstein. So after he published Tractatus Logico Philosophicus, Wittgenstein said, "Okay, I solved all the problems of philosophy." He literally says that in the foreword, in the introduction to the book. I've solved all the problems of philosophy, and I'm basically done. I'm going to move on. And he went and taught math to like young children for many years. But I guess he couldn't quite put it down, and he kept thinking about new stuff. And he came back to his Tractatus was extremely influential and popular, and he came back to, I think, Cambridge University and started teaching philosophy again. And ultimately totally rejected everything he had written most of what he'd written in Tractatus. And later, he delivered these lectures, and some of them were written down and published kind of informally. There's these books that you can get now called the Blue and Brown Notebooks. Those are these transcriptions of lectures that he gave. And then I think this is like the last sort of published work credited to him that was published after he died. This book called Philosophical Investigations. And in this book, he explores, it's sort of a rejection of his earlier work in Tractatus, and he introduces this idea of the language game in the notebooks, and he really formalizes it in Philosophical Investigations. Let's see how I'm doing. Okay. So he opens the book with a passage from St. Augustine. This is like medieval European philosopher, right, who wrote in Latin, where Augustine is kind of trying to figure out, how do we learn meanings? How do we learn what things mean? And Augustine says, well, I think I remember when I was a kid, like somebody would be pointing at something and say the word, and I would kind of go, okay, that's the name of that thing. And so words are basically names of things. Wittgenstein says that's a kind of a primitive, kind of simplistic version of language. He describes a few other simplistic versions of language. Like, for example, here's one. He says, let's imagine that there's a language where there's a builder named A and an assistant named B. A is building with these stones, blocks, pillars, slabs, and beams. And so they make up these words between the two of them. They maybe don't have any other language. They're like, this is cavemen or something. And so they make up these words to refer to these different slabs. So A says block, and B goes and grabs a block and brings it over. Now, Wittgenstein says you might think that this is a primitive idea of language, like a primitive analysis of language, or I'll call it a simplistic analysis of language. But he says, let's instead think of this as a language more simplistic than our own. And he says, don't let it bother you that they only have orders. Okay, so all you can do in this language is ask for a type of stone. And that doesn't mean that the language is incomplete. If you think that, then think about your own language. Is your language complete that you use every day? Well, you have some words in your language, like these ideas of symbolism of chemistry, notation of calculus. You didn't always know those words. Was your language incomplete before you learned those words? it's easy to imagine a language consisting only of orders and reports, only of questions and expressions for answering yes and no, and countless other things. And to imagine a language means to imagine a form of life. This is Wittgenstein's central point. The language game is a way of looking at language where we say, there may be many language games happening at once. One language game might be this one where I can name a fruit that I want from the kitchen, and my kid will go get it for me. Okay, that's one language game. And then I have another language game that I use when I'm doing math, and so on. I have another language game that I use when I'm doing the dishes, and I'm, say you're like at a friend's house, and you're helping with the dishes after dinner, and they're drawing the dishes and they pass one to you, but you don't know where they go, so they just keep passing you dishes and saying, top left cupboard, lower right cupboard, and so on, like that. That's a complete language, is Wittgenstein's point here. And the way that those all fit together and make a larger language that we use is that we can kind of like play them simultaneously and overlapping, and we're able to disentangle rules from one game from the rules of another game as we do that. Because he says that comes from our universal, our sort of like shared experience of observing other humans behaving, and we know how to interpret that because that we're social animals. He says language is strictly social. There's no such thing as an individual language. This is in contrast with, if you've read anything by Noam Chomsky on linguistics, Noam Chomsky says that language is interior, completely interior, and that we shouldn't, in order to understand language, we shouldn't study the sort of external meanings, social meanings of words. Instead, we should only study the completely intentional interior meanings of words. This is part of Chomsky's ideas. But for Wittgenstein, language is only ever social. And it's bound up within a form of life, a kind of activity that we do in life. And that's where it comes from. Language emerges from these forms of life, right? So let's move on to the next page here. Oh yeah, okay. So here are some examples of language games. Giving orders and acting on them, describing an object by its appearance or measurements, constructing an object from a description. This could be like you could imagine in like a TV cop show, the victim is describing the perpetrator to a sketch artist, and they're saying, no, his eyebrows were a little bit bigger and his nose hair was bushier or whatever, right? That's a complete like sort of self-contained language. Reporting an event, speculating about an event, making up a story, reading a story out of a book, acting in a play, cracking a joke and also telling a joke, two different language games, solving a problem in applied arithmetic, that could be like a story problem or something, praying. And he says we can easily imagine people in a field. This is just an image to illustrate the combination of language games. Imagine people in a field playing with a ball, starting various existing games, playing games but not finishing them. In between any specific games they're playing, throw the ball in the air to see how high they can throw the ball, throwing it at each other as a joke or something. And think that the whole time they're playing a ball game, they're definitely following rules at every throw. That's what language in human life is like, according to Wittgenstein. Wittgenstein's writing style in Philosophical Investigations is sort of like dialectic writing style. So he usually has some just like unnamed imaginary person whose words he puts in quotes who is arguing with him. So he says, somebody might object against me. You make things easy for yourself. You talk about all these different language games, but you've nowhere said what is essential to a language game, and so to language. What is it that's common to all these activities and makes them into language or parts of language? Okay, we're going to come back to that in a minute. So let's see, what did you say? What is something that cannot be expressed with language? Got what it's like. Yeah, this is cool. What it's like to experience consciousness. Yeah, sure. I certainly couldn't put that into words. I mean, I might be able to sort of like suggest it poetically. I think that's like a lot of what we're trying to do when we write poetry. But it's really difficult because poetry is such a sort of intentional form. It's really hard to say that it's making it. The meaning is making its way through, and most of the time it's not. And we're just sort of like wrestling with these incomplete intentional meanings, and that's the joy of poetry. It's like wrestling with the stuff that slippery, intangible stuff. And then Kurt says, information, brought by smell and taste. Yeah, totally. This is actually an example that Wittgenstein uses also. He says, how can you describe the smell of coffee to someone? Maybe in terms of another smell or something, but it's pretty difficult. Oh, and then my dad chimes in. He says, the mystical unitive experience. Okay. I don't know specifically what he means by that, but something. There are maybe kind of like the pull towards each other or something like that. Unitive, like unifying. Yeah, that's interesting. Yeah, a lot of mystical, religious, spiritual experiences go beyond language. Absolutely. Oh, cool. I heard a sound. I like this one. Right before going under for a surgery. Yeah, I have a friend who's a composer and one time told me he was trying to make these sounds that he hears just as he's falling asleep. And just weird sounds from his brain shutting down, I think. It's really interesting. Also, speaking of that, film Memoria, that's what Memoria is about. This woman hears a sound that she can't identify, and she's trying to figure out what it is. And there's in the trailer, I haven't seen the film yet, but in the trailer there's a part where she's describing it to a sound designer, trying to get him, just like the sketch artist, trying to get him to reproduce it. Yeah, and Aaron says even thoughts are nearly inexpressible. Yeah, I think it's probably true that most of our thoughts are inexpressible. On the other hand, there are some ways of looking at thought and language that where language kind of constructs thought. It's not that we're putting in, not that when we use language we're putting our thoughts into words, but that we're building our thoughts out of words that we hear from other people. This is another perspective on language. Yeah, thanks for that. So we left Wittgenstein with this kind of troublesome question. What is it that is essential to all these language games? And he says, this is true, that I haven't yet told you what is essential to all language games or to all of language. What is the one thing, like if we look at all these different things, what is the one thing that they all have in common that make them languages? Because in order for a category, to exist, there has to be something that tells you whether it's inside, whether any given thing is inside or outside the category. That's a classic, sort of classical kind of logical construction, right? He says, instead of pointing out something to common to all that we call language, I'm saying that these phenomena have no one thing in common, in virtue of which we use the same word for all. There are many different kinds of affinity between them. And I'll try to explain this. And the example that he uses is games, to explain this idea of a concept that doesn't have one unifying essential quality. And this is where I found Wittgenstein's, because I was looking at philosophy of games. And so I really love this passage. So he says, consider the activities that we call games. I won't actually read this word for word, but for example, board games, card games, sports, stuff like that. What do they all have in common? Now, don't take the easy way out and just say, well, they must have something in common or we wouldn't call them all games. No, look and see. That's metaphysics, by the way, saying, oh, well, surely they must, we're just purely using our reason and to construct this synthetic knowledge that there must be something essential to games. He says, no, don't use metaphysics. Look and see whether there's anything common to all. If you look, you won't see something that's common to all, but similarities, plural, affinities, and a whole series of them at that. Look at board games, for example, and then pass to card games. And you say there's some things the board games and card games have in common, but there are many things that are not common to the two. And then we can pass next to ball games and sports. So you can, if you say that the definition of a game is that it's a board with pieces, you can say, okay, well, you're thinking of board games. But let's, if you want to just talk about board games, that's okay. But if you want to talk about games, not all games have boards, right? Here, this is my favorite part. He says, are they all entertaining? Are all games fun? There's a lot of reviewers on Steam that would have you believe that it has to be fun in order to meet the definition of a game. This is something that we ran into with Kentucky Route Zero, of course. But he says, compare chess with tic-tac-toe. Or is there always winning and losing or always competition between players? Well, there's not always competition because we have solitaire. And not to mention video games, many of which are single-player things now. In ball games, there's winning and losing, like in soccer, there's winning and losing, football. But when a child just throws a ball at a wall and catches it again, even that feature has disappeared. And look at, if we want to say that games are about skill and luck. Well, think of the difference between skill in chess and skill in tennis. Those are completely different ideas. Then think of singing and dancing games. Those are fun, but they basically have nothing else in common with the rest of these games, right? And so we can go through these many, many other groups of games in the same way and see these similarities appear and then disappear, just like transient similarities as we explore the possibility space of games. We see a complicated network of similarities, overlapping and crisscrossing, large similarities and small similarities. And I can think of no better expression to characterize these similarities than family resemblances. Like different members of a family, like me and my dad are both have curly hair or whatever, wavy hair, but he's a lot taller than I am, and so on. There's and then me and my brother have a different set of similarities that are not the same ones that I share, with my dad or with my sister or something like that. He says, yeah, games form a family, not a sort of like category with an essentialist quality, but this new kind of concept construction called a family, which is held together by family resemblance. Okay, a family. And likewise, the kinds of number, for example, form a family. Why do we call something a number? Well, maybe because it has a direct affinity with some things that we've already called a number. And for that reason, it has a sort of indirect affinity with other things that we also call numbers. And we extend our concept of number, as in spinning a thread, we twist fiber on fiber. And the strength of the whole thread resides not in the fact that some one fiber runs through its whole length, but in the overlapping of many fibers. Just to illustrate this image, I should put us back up here. Anyway, just to illustrate this image, these are fibers. Okay, so fibers are like what threads are made out of in yarns, right? They can be natural fibers like cotton fibers or hemp fibers, or they can be wool, or they can be synthetic fibers that are made out of like plastic. These fibers, we distinguish between these like staple fibers, which are these short little fibers, as opposed to filaments, which do run the whole length of the yarn. So like a lot of synthetic yarn is actually made by extruding long filaments and twisting them together into a long single yarn. And your whole sweater might have one might have a filament that runs through the whole thing. But natural fibers and also lots of synthetic fibers are these little pieces. They get sort of like wound together, and they get wound together spun together in this process. This is a spinning wheel. You can see she's kind of like feeding in a bunch of, first there's all this preparation that you have to do to get the wool or whatever ready to spin, and then you can make a single thread out of it. So I want to think about this question of this idea of numbers, the way he talks about numbers here. So what the heck is he talking about? The kinds of numbers form a family. Is there really not like some essential quality that runs through all of what we call numbers? So here's our special guest for today, my dad, who is going to give us some insight into numbers and math. His name is Connell Elliott, and he's a mathematician and computer scientist. I think I've told this story in the past about Kentucky Route Zero, that like this is kind of where I first encountered the game Colossal Cave Adventure. It was when my dad was a student at Carnegie Mellon, and he was studying computer science there, and we had a terminal at home, and we played the game together. I'm just going to open his webpage a bit. This is connell.net is his webpage if you want to learn more about him. This was a part of a paper that he wrote in the 90s when we were kids, and he used photos of us to demonstrate these animations that he was programming. So I talked to him a week ago or so. Let's see, do I have this? Oh yeah, no, I've got to open up VLC. And I asked him a bunch of questions about math and numbers to try to give us a sort of like kind of expansive, but sort of context for the rest of our conversation about numbers and algebra as they relate to computer programming, which we're going to get into a little bit more in the next session. So I'm just going to play these, and I'm going to mute my microphone, and then we'll come back and kind of talk about them and connect it.
What is a number? I don't know. I don't know if there's any kind of one thing that a number is.
Yeah.
I think they're like used for different things, and then the different uses maybe kind of point to different flavors of numbers.
Yeah.
So there's the how many something. Yeah, and that's usually a natural number, meaning 0 or 1 or 2 or so on.
Yeah, or counting numbers.
Yeah, counting number.
Yeah.
Yeah, and uh, then there's how much as opposed to how many, which is more like a real number. So, you know, in other words, it could be fractional, it could be 2/3 of something or something like that. You know, if there's two of us and we've got some carrots or maybe some blueberries are a little more uniformly sized, we might want to divide them evenly. And if there's 32 of them, that's fine. If there's 33, that's kind of problematic. Right? There's two of us and 33. Yeah. So then we have to decide, do we just not get to do this thing, or do we have to make up some kind of a number that is between 16 and 17? Even some fractions, like if you were to write them in base 10 or whatever, hard to write down a fraction in base 10. If it's like a third, there's no finite way you can write it down. I mean, there's no finite you have to invent something in order to have a finite way to write it down. And that's the idea of repetition, of like 3 repeats, or maybe 1/7. There's I can't remember how many digits, the sequence of digits that repeats. And yeah, so all rational numbers have that property. You can write them down in base whatever. And you'll get something that if you have a way of saying this segment repeats forever, then that little technique, throwing in that language extension, gives you a way to describe it finitely.
Yeah.
But other numbers, like the diagonal of the square, there you can't do that. You still extend the language. Square roots and fractions are both ways of answering the same kind of question, which is, what are the solutions to this equation? All right. So if it's like 2 times x equals 5, that's your equation, then you're not going to get an answer if x has to be a whole number, but you will if it's allowed to be a fraction. And then if instead you say like x squared equals 2, and that's the equation for that diagonal. If you got 1 and 1, it's x squared equals 2. Then you go looking for fractional answers, and you won't find them.
Right.
Yeah, and you can like look at it and say it does seem to have a length. Like I'm looking at it right in front of me, right? And it looks like other things whose lengths are numbers. So what's going on here? Yeah. So we had to invent the idea of these numbers that aren't ratios. There's the utilitarian aspect. This is like motivated by some practical thing I'm trying to get done. Yeah, but then it becomes an intriguing kind of system in itself, and then we start poking at it, and then we find things that are missing from it.
Yeah.
And we might not have been looking for those things at first, but they still are appealing to go kind of, some of it is maybe like collect them all. It's like I have this collection, I kind of grow fond of it, and then I want more esoteric, things from my collection.
Yeah.
Kind of rarities or something like that. And somehow these things that we discover by filling in gaps inevitably seem to be useful in a practical sort of way. And then there's this other aspect of numbers, which is these numbers have certain properties that you can write down. Yeah. So then what's useful vocabulary? And with numbers, it's usually things that are somewhat like in the neighborhood of 0 and 1 and plus and times. So that's a vocabulary that's shared by the natural numbers. Yeah, they have all those. Some people say the natural numbers don't have 0, but that's just a matter of what you call them. And rationals have those, and the complex, which is, and that's non-trivial, because like in complex numbers, they're not one-dimensional anymore, right? And so like, what does it mean to add 2 of them or multiply 2 complex numbers? And they live in the 2-dimensional plane. I mean, they don't really live there. That's a way we realize the 2-dimensional plane. And so and as you said, they have like a real part and an imaginary part. And when you add them, it's the formula, the mechanics is fairly simple. You add the real parts, and that's the real part. You add the imaginary parts, and that's the imaginary parts. When you multiply them, it's it's really intermingled. It's this sum of products kind of a thing. You have to get creative about what addition and multiplication means. But if you make good choices, then it turns out that they behave remarkably similarly, even though they have like all these weird numbers that never had before. And so these properties are things like we have zero and we have addition. And if you combine those two, you say zero plus X, you always get X. That's the law identity. Or if you do X plus zero, you always get X. And then there's this other property which just involves addition, which is if you say A plus B, you take the result of that and add C. That's the same as if you added A to the result of adding B and C. So which way do you kind of group them? And those two are equal. And that's also true for complex numbers. It feels like it's a weird numerical thing, but it's still kind of, and then it's like you could think of it as a couple of numbers. And so it's, at least it's pretty numeric, maybe even more so. But you can look at things like languages or pictures or sounds, and those also have operations that have these same kinds of properties. That you can identify something that you might want to call zero because it goes along with the other thing that you call plus, and it has these properties. The associative, that's the one where you regroup, or the identity, where the zeros vanish when they get added. If I want to think about what's true. So that's a specialized areas of philosophy and mathematics, right? Science in a different sense.
Right.
What's true of the universe? Yeah. If I want to know what's true about mathematical things, so mathematical notion of truth, then I'm going to have to do some reasoning, and that reasoning is going to include, if I'm reasoning about numbers and I want to say prove that addition is commutative. Right?
Yeah.
Then I'm going to have to be really clear about what exactly a number is and what addition is and what zero is, and then I'm going to have to somehow check. And it's not going to be just an exhaustive check all the cases, because there's infinitely many. Right? There's going to be some other systematic way of doing these proofs, like proof by induction and things like that. So if my job is to know what's true, either because I'm just interested in that, or because I want to build an airplane that doesn't crash, or a rocket ship that actually gets to Mars or something like that, right? Knowing what's true wherever I can is an advantage. Then I'm going to have to do these proofs, these reasoning, these steps of reasoning, and it's complicated and tedious. So but rather than just giving up on the enterprise, I'd like to be able to reuse work that I've done for other purposes. Okay.
Yeah.
So that's what these patterns enable. The patterns that we say, it's worth calling this pattern a monoid or a semi-ring or something like that, because then I can talk about all such things, all semi-rings, and I can, in some cases, prove things that are useful and true of all semi-rings. And then when I go to a particular semi-ring, like a real numbers, then I don't have to prove it for that special case. I have to prove it's a semi-ring, and then every fact that has already been proved true of all semi-rings has to be true. Yeah. For efficiency, we have tried to find reusable building blocks out of that reuse in a variety of ways that we can design carefully and not have to figure out from scratch every time when we make things, or making a thing, or making a knowledge about a thing. In other words, truth. They have the same algebraic structure, but if there's maybe a little more to it, they have the same they speak the same language, they obey the same laws, but they're also related to each other in that, say there's a mapping, that there's a function, there's a way to transform one into the other, and where that translation preserves the language, and I'll say what I mean by that, the common language, that's called a homomorphism, which just means same shape. Homomorphism, same shape. Yeah. And so an example of that, actually, there is one with the plus and times games. If you take, define a function, which is I'm going to raise 10 to the power of, doesn't have to be 10, it could be 2, whatever. But let's say 10 to the power of, that's my function. So power of what? That's the argument to the function. Okay. So if I raised 10 to the, and then if I raise 10 to the 0, okay, so apply that function, 10 to the 0, I get 1. Okay. 0 is the identity for addition, and 1's the identity for multiplication. That's cute. What if I raise 10 to the, and then I use addition, 10 to the x plus y. Let's say 10 to the 3 plus 4, right? 10 to the 3 plus 4, that's 10 to the 7, which is 10 million. Right? So what if I take 10 to the 3? That's 1,000. 10 to the 4 is 10,000. I multiply those together. That's 10 million also. That's pretty interesting. So if I take this 10 to the, and I apply it to an addition, I get a product. If I apply it to a sum, I get a product. So it turned my 0 into 1, and it turned my plus into times. And so that's an example of a homomorphism. So, in other words, we have these two monoids. They're both on numbers. One is 0 and plus, and the other's 1 and times. And then we have this function that turns one world, the plus 0 plus world, into the times world, 1 and times. And that's actually exactly how slide rules work. So slide rule is mechanical. You've got these like 3 things, and the one in the middle is slides freely, the 3 bars. The top and bottom are kind of rigidly attached to each other, some kind of bracket. And then you've got one in the middle that slides, or you could rotate, but let's talk about the sliding one. And then there's this transparent little thing. It's kind of a window you can move, and it has this fine red line in the middle. And that's what you like line up with your eyeball, and they have very precise markings. And so they're for multiplying numbers before you have calculators. And the way they work is with this homomorphism, which is I want to multiply numbers. That's hard. And it's not obvious how you can use mechanics to multiply numbers. I think with pulleys, you can do multiplication somehow. But with sliding, I don't really know how to do that. But you can do addition pretty easily by sliding things, which is, you like have some mark, and then you move this over, and so that like the end of one and the beginning of the other coincide. This is a very mechanical thing.
Yeah.
And then you look how much, So you can do addition by sliding, but I want to do multiplication. So if there was only some way of translating between the worlds of addition and multiplication.
Yeah.
And that is exactly what a slide rule is. And that's why the spacing of the numbers on a slide rule is so weird, because the spacing is exactly that exponentiation function. Every single thing I ever design is based on this principle. I think it took me a very long time. I think I must have been clued in somehow intuitively to this idea of analogy. And I had learned about denotation semantics, and I kind of used it, but I hadn't really put my finger on the analogy aspect until crikey, now I don't know, maybe it was 10. Well, no, it had to be more than 10 years ago, maybe 17 years ago, something like that. And I stumbled on it entirely by accident through poetics. And I was writing a paper on something. It was a technical paper, but I loved the ideas I was talking about, and I wanted to be able to express them not just accurately, but in a way that like spoke to how I feel about them, the kind of the beauty and excitement I feel about them. And so I kind of caught a little whiff of a pattern that was like poetic, that had the kind of, like the even meter, and maybe rhyme isn't quite the right word, but there was some kind of balance or counterbalance that it just made the expression sound really pretty. And now I know that if I ever don't find them, that there's actually something wrong. It's not just like a pretty thing to add. It's that now I believe that the very act of programming or creating, whatever, is analogy making. That we use computers exactly for that purpose, to form analogies to something else. And that something else could be like, music isn't computation. I mean, it is by physics, but it's certainly not digital computation, right? But if I wanted to write a program that generated music, or, visual, right? Then I'm doing something on a computer that is analogous to something that is in my mind that's visual, right? And so wouldn't it be nice to be able to talk about analogies precisely? And that's what homomorphisms do. It's really practical too, because it means like I can have it like you were saying, what Chris Strachey, or was it Dana Scott, or maybe both of them, pointed out about, decide what a language means before you decide how to implement it. And this isn't just language, it's anything we do in programming, anything we build, like decide what its job is before you try to get it to do that job. And then I would say add to that, and I think that's what you were saying too, is don't let those two different aspects of interest, what it means and how it works, don't let them contaminate each other.
Right.
Because they're so different. Like what makes a program effective is it like it actually runs on a computer? Okay, well, that's a big compromise, figuring out how to get something to run on a computer. That,
Right.
also maybe it does it fairly efficiently. So you maybe have some clever algorithm, but what it means, should be like elegant.
Mhm.
So we're optimizing for different things. We're optimizing for using machine efficiently, versus we're optimizing for understanding and thinking about efficiently, either informally or formally. And those
Right.
two they pull in such different directions.
Right.
And when people don't make the distinction, which is most of the time, they always end up with some weird compromise that does both poorly.
Right. Yeah.
Yeah. Yeah. And without understanding that there are two things that you can cleanly separate and then connect via homomorphism. That's the glue.
Mhm.
That's a connection.
Yeah.
Yeah.
Cool. So that I edited that down from I interviewed him for like a little over an hour and for this recording, but I put the whole unedited recording in that Google Drive if you want to listen to it. And I also would say if this is something like, especially if you kind of maybe are already versed in computer science kind of stuff. My dad recently did this interview with a podcast too that is quite long. It's 3 hours long. I only listened to 2 hours of it. Sorry, Dad, but it's quite long. But it's really good and interesting, and it goes into more depth than we did in these clips, in some of his ideas and how they show up in computer science, or how they anyway, his ideas. So I've been talking with my dad a lot about this stuff. Because as I described in our last session, it sort of started out for me as like just trying to figure out how to write a parser, how to make a programming language, and I got more into the math and stuff once I got to this point where I had a parser for my language. I had the syntax formally defined completely, and then it was like, what does it do now? And I just didn't have any point of reference for a kind of meaningful interpretation of it, and so I went back to thinking about what is what could be the meaning of this program, and anyway, that kind of came up in our conversations. He pointed me towards this denotational semantics work of Chris Strachey, and that's where that stuff's coming from for me. So we're gonna get into some of the things that he mentioned there. If you listen to the full recording, if that's interesting to you, we don't the full recording that I put in the Google Drive. It's an hour long, but we talked through what these things mean, like the monoid and the semi-ring, these terms that he used in there. We're also going to, in our next session together next month, we're gonna spend some time with these structures, the monoid and the semi-ring, and we're gonna play with them like they were Play-Doh. We're gonna get into Unity next time, like we're gonna actually write some code and run it and learn how to use Unity as a sketchbook to experiment with code. And the experiments that we're going to do are trying to find out, like, what are these things? What are these algebraic structures, and how can we mess with them? How can we play with them? How can we transform them into each other, and so on? So thanks, Dad, for being my first guest in this workshop. I really appreciate it, and I hope you enjoyed those clips talking with him. One thing that he talked about was this idea of like, we are doing things with numbers, and then we find that we need new numbers because either, in his example, either like we need to divide something up in a way that our numbers don't allow us to, like the natural numbers can't, 2 can't be divided by 3 if we're just using natural numbers. So we had to invent this new number, this new kind of number, a rational or real number that can be written either as a ratio of natural numbers, or in this like sort of decimal form, or in some of these other forms like the repeated digit format. Then we start asking more complicated questions, like just as math questions. We start asking, like, if I times I equals -1, what's the value of I? Our idea of like something times itself. If you want to know like x times x equals 4, we don't want to know what x is. We can figure out that's 2, but we don't really have an answer for when it's a negative number, because -2 times -2 is +4, right? So we start discovering numbers in the context of the math game. We say, oh, okay, there is a number, it's called I. It doesn't really have a value that could be described in any of these other number systems, can't be written down in this way. But now we can kind of do math with it and use it in the game. And then we discover, like, holy shit, this describes electricity. It describes quantum physics. We find things in reality that are described by these numbers that came into being as pieces in a game, sort of like the Matrix or something. It's pretty exciting. So here's a little diagram I just found online of the numbers. This is like number theory about the different kinds of number and how they form a family, right? So, and you can see in this diagram, there are some diagrams online that look just like this middle part here, where everything is nested, and it's like, counting numbers, and then there's a superset of counting numbers called whole numbers, or that's in this formulation. These two together is what my dad and I were calling natural numbers, and is standard terminology. And then we have integers, which is where we add this operation of negation, where you can have a negative, and then if you add a negative and a positive, that's like how you do subtraction. And then we have rational numbers. But you can see here that some of, it's not like all numbers contain these counting numbers. It's not like they're all just like successive, like the nesting dolls. It's not like that. Some of these numbers, like these imaginary numbers, are not part of this set over here. This is the way that, as Wittgenstein said, there's no one fiber that runs through the whole thread, right? The whole yarn. These are some examples of these algebraic structures, and I just wanted to kind of illustrate it a little bit. And again, we'll get into this in much more depth next month. But these are some names of some different structures. They really just name, like, you have a set, like, for example, a set meaning like it can be infinite or it can be finite. The set can be the values true and false, 1 and 0. Those could be sets, or the set could be the natural numbers, which is infinite, right? It goes on forever. So you have the set, that's one thing, and then you have an operation, and then we'll add more to that. But to start with, let's call these like group-like structures, or where you have one set and one operation. And so an example of that is this one called a monoid, which sounds like something from Doctor Who, but it's actually an algebraic structure. And a monoid is anytime you have a set where these rules are true, and these rules don't necessarily have to be true. So for natural numbers, they're associative. Natural numbers with plus, we'll say. You can add them in either order, like 1 plus 2. 1 plus 2 plus 3 is the same as 1 plus 2 plus 3, right? There's a 0 that you can add to anything and get 0 again, but there's not negatives. Actually, natural numbers with addition are commutative. 2 plus 3 equals 3 plus 2. Anyway, but doesn't necessarily have to be. So yeah, we'll come back to those. Oh, and I really just wanted to show you a slide rule in case you've never used a slide rule. I have never used a slide rule, a real one. I bet Tomas has. I'll ask him. It's the kind of thing he would be into. But this is a slide rule, and my dad was describing this as an example, physical example of a homomorphism, which is where you can kind of create this precise analogy between two structures. Right, so this is how a slide rule works. And I just kind of wanted to demonstrate it. So again, like, you can add numbers with two rulers, right? You put them next to each other, like you said, and then you slide one up, and then you can kind of go from here to here, and then from here to here. So it's like kind of like splitting into two parts, right? Splitting a counting process into two parts. On the slide rule, there's like all these different rows that mean different things. Let's look at just the C and D here. And this middle part slides freely, right? And then this little indicator is for just to help you find stuff. So for example, so you can use the slide rule. I'm just going to multiply 1.5 times 2. That's an easy one because I know the answer to that is 3. Okay, so what you do is I'll find 1.5 here on the D, which stands for decimal. And I'll find 1.5, and then I'm going to slide this middle one, not that one, but this one, until the 1 here, the beginning of it, is on the 1.5. And this is actually already making a statement. This is saying 1 times 1.5 is 1.5. But I want to do something slightly more interesting than that. So what I want to do next is I want to drag this guy over. I hope I did this right, because this is kind of, again, I've never really used. Oh yeah, cool. Okay, so I slid over here to start at the value on the bottom that I want to multiply, and now I'm going to look over on this row, the middle one here, and find the 2. So again, this is 1.5 times 2. I'll use this to line it up, and I can see there. Okay, yeah, 1.5 times 2 is 3. That's doing math with a slide rule. And you sort of have to like like, I could say this is 1.5, but I could also think of this as 15, and I could just like multiply it by 10. So you can do this, for lots of numbers. And then if I wanted something in between, like 1.73, I could find these little, markers. That's why the sliding guide is really useful for this one. Okay. So that's an example of a slide rule. And then here's some other things. We'll look at this stuff next time. I put too much stuff in here. This is just to, pause the video if you want to read this. I'm trying to move fast to wrap up. But this is Wittgenstein kind of using his dialectical writing style to think through this idea of the number and the game being concepts that are not just, they're families. Remember, these are conceptual families. But he also says these concepts are not closed by a boundary. So we might still find more numbers, and it doesn't mean that we didn't have numbers before, right? Just like he was saying with languages. When was your language complete? If you point to any part of your language and, if you say, no, you can't say no language is complete without calculus or without chemistry, symbols of chemistry or something like that, right? Because you had a complete language before you learned those things. So it's not that, yeah. So this is him kind of like talking through that idea. And then I put these notes in the Google Drive, these slides. And there's a couple links here in the end in case you want to kind of like look ahead, or maybe you're already pretty comfortable with math or algebra or programming. If you want to look ahead, these are some resources. I really like this group called Socratica. They have like a lot of videos on YouTube, and I support them on Patreon. Their series on abstract algebra is super good if you learn better from videos than text. This is a textbook. This is the one that I read a lot by this guy named Pinter, and it's called A Book of Abstract Algebra. It has a really nice, I recommend you read just at least the introduction to this book, because it's a really nice history of algebra. But I also put a copy of this in the Google Drive. This is that podcast that I mentioned that my dad was on, where he can go into a lot more depth. He has a lot more room there, 3 hours of room to go into more depth. I cut him down to 15 minutes on this time, sorry. And then this is a video, really cool video on the channel Numberphile, a YouTube channel called Numberphile, which is about just like a cool math channel. This is a video about transcendental numbers. This is a really fun one, even if you're not super into math, where this Australian mathematician explains what are transcendental numbers, like pi and e and some of these other kind of really wild numbers. So yeah, highly recommend that one. Here's your homework for our next session. Let's see, come on, what's going on? Yeah. So experiment number 2, we're thinking about Wittgenstein's maxim, to imagine a language is to imagine a form of life. So the first part, you can do either one of these or both of these or whatever you want. The first part is I started a document in the Google Drive called the Language Game Database, and I put in some examples from Wittgenstein, and I'd like you to contribute some examples that you find just in your life of language games that you see in here. It can be a really interesting challenge to disentangle language games in the wild. So that's what I want you to try doing here. And just write up, what are the rules of this game, or write a little narrative about what you saw happen, or however you want to frame it, a poem. You can just write it as a game design document if you want. Anyway, it's just a Google Doc, and go ahead and add in your examples of language games. The second part is to write a short piece of fiction in the form of rules for a language game, which suggests a form of life. So I want to leave this one pretty open, but this is more of like a creative writing prompt. Imagining a form of life by imagining a language game. And then the other part of your homework for the next session is in the bookshelf folder in the Google Drive. I put a copy of this essay called Epistemological Pluralism. Epistemology is like a form of knowledge, a way of knowing. So epistemological pluralism is about making sure that there's space for multiple different ways of knowing within one kind of teaching context, is the context of this text. This is written by Sherry Turkle and Seymour, I don't know how to pronounce his last name, I've always wondered. Papert? I don't know. Seymour P. also wrote a book called Mindstorms, which I put in the Google Drive also, a copy of that. And he worked on a language called Logo, which was a teaching language for children to teach them programming. It's based on this idea of constructivism, in education. So we'll call this constructivist pedagogy, which is about like playing with things, working with things in order to learn concepts. And that's what this paper, this essay is about. Sherry Turkle is a writer who wrote a lot about computer culture. She's a sociologist and psychologist, and she wrote a lot about like how computers change the way we relate to each other. I think a lot of her biggest works came out in the 90s, but I believe she's still writing. And so this is an essay that they wrote together. You can find it. You can just find it online too. There's a few different versions of it online, but there's a copy of it in the Google Drive too. I'd really like you to read that because this is the basis for how I'm going to approach the teaching of programming and abstract algebra in Unity. So I just want you to know where I'm coming from, and I also just think it's interesting. Also, if you I want to hear your responses too. If this paper's kind of dated in some ways, but it's also super interesting and rich, and I just would really love to hear your responses, positive or negative or critical or anything that comes to mind when you're reading this. And I believe I made a Google Doc in the folder also for you to add your thoughts to. Next time we're going to get into Unity. We're going to learn how to use Unity as a sketchbook and how to build algebraic structures and play with them. Thanks again so much for joining me today. I think we're just going to say these things are 90 minutes long. I'm always aiming for an hour and coming out at 90 minutes, so we're just going to say these are 90 minutes from now on. Seems to be the natural pace of things. Thanks again, and I will talk to y'all soon.